Hey there, we are going to talk the law of conservation of energy. Now, you may have heard of this one, it's kind of a big one for physics. Just like momentum, energy is conserved, and that means it cannot be created, it cannot be destroyed, it has to all be accounted for, and this is very important. So, energy can be transferred. It's transferred when one object loses energy and another object gains that energy. And so, again, we're accounting for it. One object losing it doesn't mean it's destroyed, it just means it's going to get gained by another object or system. And so, examples of that would be when you have hot coffee in a cup. Some of that thermal energy is going to get transferred to the cup from the coffee, so the coffee loses that thermal energy, but the cup is taking that thermal energy, so we are accounting for it. We know where it went. A billiard ball, when you're playing pool, you hit a billiard ball and it is going to hit other billiard balls, and that is going to give some of its kinetic energy to those other billiard balls, which means that it's losing that energy, but the other billiard balls are gaining that energy. So again, we're accounting for all of that energy. Now, energy can also transform. Energy is transformed when one form of energy becomes a different form of energy. And so we see this all the time, for example, with cars braking. You have all of this kinetic energy that a car has from its motion. That kinetic energy is transferred to the braking system when the braking system is engaged. This slows the car down, so the car is losing kinetic energy, but again, it's not destroyed, it's just being transformed into a different type of energy. And we can see in the GIF here that that is thermal energy from the glowing rotors inside the wheels. Another example would be a swinging person on a swing. They have a lot of kinetic energy at the bottom of the swing, but as they start to climb, they start to slow down. They're losing kinetic energy. Where's it going? It is actually transforming into gravitational potential energy as they start going higher and higher into the swing. And this repeats over and over as they swing back and forth. Now, energy is transferring and transforming all the time, all around us. For example, your food has chemical potential energy that is transferred to your body when you eat, and your body transforms this into kinetic energy like when you move. Another example is photosynthesis. Radiant energy is transferred from the sun to plants, and the plants use this energy. They transform this energy into chemical potential energy, which gets stored in the bonds of the glucose that they make for food later on. Chemical potential energy in gasoline is transformed into kinetic energy when you burn it, and that is transferred to cars, which is how they move. And finally, electrical energy from your stove is transformed to thermal energy, which warms your stove, and then that energy is transferred to your food, which cooks your food. Now, no matter what energy is transformed or transferred in and out of a system, it all must be accounted for. Just remember, energy cannot be created nor destroyed. You have to account for all of it. Now, oftentimes in energy conservation, with transferring and transforming, this involves heat. And so heat is often lost from systems and objects. And so energy that leaves your system as heat isn't destroyed, it's not just disappearing. The energy from the system or the object was converted to thermal energy, which was then transferred to surrounding objects or systems. Now, when a system loses energy as heat due to, say, friction, for example, that energy is no longer available as potential or kinetic energy. An example of this is when a car uses its brakes. So in this example, the Lamborghini has a lot of kinetic energy, and as it's approaching the turn, it's slowing down. It's using its brakes. Now, brakes rely on friction to slow vehicles down, and where there's friction, there is heat. And so the brakes are working to get rid of some of the kinetic energy of the Lamborghini, but we have to be able to account for that kinetic energy. So where did it go? Well, the energy isn't lost. That kinetic energy is being transformed into thermal energy due to the friction of the braking system. It's transferred to the brake rotors, which we see glowing red in the GIF on the screen, and then that thermal energy from the brake rotors is transferred out of the car system into the surrounding air around the car. So it's leaving the car system. As the car exits the turn, it's going to need to speed up again, but it no longer has that kinetic energy that it used to. So where are we going to get more? Well, we have another useful form of energy stored in the gas tank. Gasoline stores chemical potential energy in its bonds. And so when you burn gasoline, you're releasing that energy. It becomes kinetic energy, which can then be transferred to the car to speed it back up. Here's a simplified explanation of all of those transfers and transformations if you want to pause the video and take a closer look. Now, as we just saw, a typical gasoline-powered car loses all of its kinetic energy to the environment as heat. Regenerative braking is a technology that utilizes the kinetic energy of a car to recharge the batteries of hybrid vehicles. And so regenerative braking transforms some of the kinetic energy of the car back into electric potential energy that can be stored in the hybrid car's batteries to power the hybrid vehicle's motors. Now, when we're applying the conservation of energy, we should always try to account for all energy transferred and transformed. Oftentimes, though, you're going to see in physics problems to ignore air resistance and ignore friction. And why do we do that? Well, it's because both of those things involve thermal energy, and thermal energy is rather hard to keep track of. All energy is still present. Thermal energy is no exception to that. It's just, again, very hard to track. So let's take a look at an example, so I'll show you what I'm talking about. In this example, we have a 50 kilogram box and it is sliding across the surface. And when the GIF resets, you'll see it starts at 40 meters per second. So we can actually calculate the kinetic energy of the box when it starts. Now, at some point, the slider turns friction on and we can see that the box starts to slow down. That means kinetic energy is decreasing. Does that mean it's lost? No, it just means that it's being transformed into thermal energy and transferred to the box and the surface of the path. Now, if we wanted to assume that all of the kinetic energy became thermal energy, we could just simply find the difference between the kinetic energy that the box started with at 40 meters per second and the kinetic energy that the box ended with at 0 meters per second. But again, that would be assuming that all of the kinetic energy became thermal energy, and we don't know that for sure. Some of it may have become sound if we heard the box sliding. It's not very easy to test the box and the path to see how much thermal energy they have either. That's not a very practical way to go about this. And so because of these complications, since we're beginners with conservation, we choose to ignore things that result in thermal energy like friction, air resistance, drag, to simplify the problems for now. In this side-by-side example, we are showing what happens when we don't include thermal energy. So because this is a simulation, this is possible. On the left side, we see that there is no thermal energy there. We're assuming there's no friction. And since none of the potential or kinetic energy is transforming into thermal energy, the energy stays as potential and kinetic, and therefore the skateboarder will continue on forever. On the right side, we have friction turned on, and where there's friction, there's thermal energy. So as the skateboarder moves, some of the skateboarder's kinetic energy is constantly being converted to thermal energy, and you can see the thermal energy bar slowly rising throughout the entire trip of the skateboarder. So because this kinetic energy is being transferred to thermal energy, which is no longer useful, eventually the skateboarder stops because they run out of kinetic energy. And if they don't have kinetic energy, they can't make it back up the hill and therefore can't build up potential energy. So in the end, all of the energy has transformed into thermal energy. Now you'll notice in both sides, in both examples, the total system energy remains constant. It's fixed. And so no matter what type of energy is currently in the system, the total system energy remains unchanged. And that is conservation of energy. No matter what's being transferred or transformed, the same amount is still there. Let's keep using the skateboarder example without friction. So you'll notice that the maximum speed of the skateboarder is always at the bottom of the ramp where height is 0. And so all of the energy of this in the system has become kinetic energy. And you'll notice that the skateboarder always reaches the same height on both sides where velocity is 0. And that means all of the energy is transformed into gravitational potential energy. So think about it like this. If height is 0 at the bottom of the ramp, then gravitational potential energy must be 0 as well. Well, it had to have gone somewhere. It can't be destroyed. And so that means it must all be kinetic energy. So where gravitational potential energy is 0, all of the energy in the system must be kinetic energy. At the top of the ramp, it's the opposite. Where velocity is zero, there is no kinetic energy at that point. It had to go somewhere, and it's been transformed into gravitational potential energy. So everywhere in between on the ramp is going to be a mix of kinetic and potential energy, but you'll notice that the total system energy is always the same. That is conservation of energy. We're accounting for all of the energy, regardless of what type it is. The total system energy remains the same. Since this is a simulation and we know it's an isolated system, no energy is leaving the system, and this is why the total system energy remains unchanged. So let's use what we know so far to try to do a little bit of analysis with the skater. What do you think will happen here? Do you think the skater will make it over the hill? Pause if you want to think about it for a second. Not quite. Well, what if we made the ramp steeper? Well, still not quite getting there. But why? What is happening here? Well, if we take a look at the energy that the skater started with versus the energy that they're ending with at the top of the hill, or that they would need to get to the top of the hill, we can see that they end up with more energy than they started with. Now, unless something is doing work, like say a motor or somebody pushing on the skater to get him up the hill, it would not make any sense for the skater to end with more energy than they started with. This system has unaccounted for energy, and that would violate the law of conservation of energy. So what can we do here? Well, we can add more energy to the system, and we could do that by putting the skater at a higher position to start with. Remember, potential energy is equal to mass times gravitational acceleration times the height of the object. So more h, more height, is going to result in more potential energy. There we go. All right, so let's do some practice calculations. So we're going to assume that the roller coaster shown in the picture here is pulled up to point 1, and so right here, with a chain, and then comes to a stop at point 1 before moving down the slope. So they're basically starting with zero kinetic energy at this point. And so go ahead and attempt these problems. If you want to pause the video to attempt these problems, do that now. I'm going to go ahead and show the answers now. Now, using the law of conservation of energy can be helpful if you need to find unknown values like, say, mass, height, or velocity. So let's say that the mass of this cart is 250 kilograms and it has a height of 30 meters at point 1. So at this point here, it's 30 meters above the ground. We're going to also assume that no energy in this system is lost to heat. So everything is either kinetic or potential. Go ahead and give these questions a try. You can pause the video and I will go ahead and display the answers now. All right, now number 2, you might have thought you had to do some math, but because energy is conserved, we know that at the top of the coaster track, all of the energy is gravitational potential energy, and we can calculate that knowing the mass, gravitational acceleration, 9.8 meters per second squared, and the height. At the very bottom of the track, where height is 0, all of that initial gravitational potential energy has become kinetic energy, so the numbers should be the exact same. You don't need to do any math for that. Now, in terms of finding the velocity at point 3, this just becomes an algebra problem. Because we know the kinetic energy at point 3, our unknown is velocity, and so we just have to rearrange the formula to solve for the unknown velocity. Here's a few more practice problems. Go ahead and pause, and I will show the answers now. All right, so once again, we see that the height of the second hill is greater than the height of the first hill, and so therefore the car is starting with the amount of energy here. It would require more energy up here, and so it would not be able to make it up this second hill. That would violate the law of conservation of energy. Here's a couple more practice problems. Go ahead and try those on your own. Pause the video. I will show the answers now. So continuing with energy conversion, potential energy to kinetic energy conversion. Let's take the example of jumping out of a burning building. If someone were to jump out of a burning building, their gravitational potential energy at the top would be turning into kinetic energy as they fell. And we're going to ignore air resistance, a source of friction, for this example again, and therefore we have no energy lost to heat. So at the top, their energy is 100% gravitational potential energy. They have no kinetic energy. They have not started moving yet. Halfway down, their energy, their gravitational potential energy has dropped to half of their energy, but the other half is now made up of kinetic energy. And at the very bottom, just before impact, they're moving at maximum velocity, zero height, and therefore they have no gravitational potential energy, but they have all 100% of their energy is kinetic energy. So using that, let's do these practice problems. The total energy of this person must be 10,000 joules at every point in their fall, since that is how much energy the person started with. Again, conservation of energy. Go ahead and try these problems. Pause the video if you'd like. I'm going to show the answers now. Let's take a look at this one. The jumper's either going to have potential energy or kinetic energy. Remember, no energy is lost to heat. This means that the sum of their potential energy and kinetic energy equals their total energy. So if the jumper has 100% potential energy at the top of the building, they must have 0% kinetic energy. This is going to be helpful. Now, as the jumper falls, their height is decreasing. When they fall half of the way down the building, they're only going to have half, or 50%, of the gravitational potential energy that they started with. Well, where did that energy go? It became kinetic energy, because as the jumper falls, the jumper increases velocity, and kinetic energy is increasing with that. So at half the height that they started, they're going to have half the potential energy, but now they also have the other half of their energy made up by kinetic energy. At the very bottom of the building, at the moment just before impact, height is 0, therefore gravitational potential energy is 0, and that means that all of that initial gravitational potential energy was transformed into kinetic energy. So at the very bottom, just before impact, kinetic energy is 100% of the jumper's total energy. So let's look at the problem again after seeing that graphic. How much kinetic energy do they have 1/4 of the way down? Now, if they've fallen 1/4, or 25% of the way down the building, they've lost 25% of their height, and that means they've lost 25% of their potential energy. Well, where did it go? It became kinetic energy, because remember, as they jump out, they start increasing velocity. That's increasing kinetic energy, and that kinetic energy has to come from somewhere. So again, if they've fallen 25% of the way down the building, they've lost 25% of their height, and therefore lost 25% of their gravitational potential energy, which became kinetic energy. So the answer to this question, they have 25% of their total energy as kinetic energy, which is 2,500 joules. Halfway down is a 50-50 split. Both gravitational potential energy and kinetic energy have to be equal, and they have to total 10,000. So 10,000 divided by 2 is 5,000. And so both potential energy and kinetic energy are 5,000 joules apiece. At 3/4 of the way down, they've lost 3/4, or 75% of their height. That means they've lost 75% of their potential energy, and that 75% loss of potential energy is a gain of kinetic energy. 75% of their energy is now kinetic energy. So that answers our question. 75% of total energy, 10,000 joules, is 7,500 joules. And finally, at the very bottom, just before impact, 0 height, 0 potential energy. That means all of their energy must be kinetic energy at that moment, and therefore total kinetic energy is 10,000 joules. I have one last practice problem for you. This one actually does account for thermal energy transformation. And so in this case, the 70 kilogram skater starts at the 6 meter mark and drops in on the ramp, goes all the way around, and ends up at the 4 meter mark at the other side of the ramp. How much of their initial potential energy at the top of the ramp was transformed into thermal energy. Go ahead and pause the video if you'd like to try this. I'll show the answer now. Now, if you weren't sure how to approach this, think about it this way. If there were no thermal energy transformation, the skater would have started at 6 meters on the left side, went all the way down, and made it up to 6 meters on the right side as well, and they would have kept doing this over and over. Because there was thermal energy transformation, some of the gravitational potential energy that was converted to kinetic energy as they moved down the ramp was also converted into thermal energy. And so they didn't have enough energy once they got to this point to go any further. Again, had there been no thermal energy transformation, the skateboarder would have went all the way up to 6 meters on the right side. They only went to 4 meters because the energy needed to go the remaining 2 meters was used up as thermal energy. To figure out just how much energy that is, we need to find the difference between the gravitational potential energy that they would have had at 6 meters and the gravitational potential energy that they ended up with at 4 meters. I hope these slides helped. If you have any questions, please ask. Please get extra help if you need it. Thanks a lot for watching.